Welcome to Algebra 2. Today we've got section 5.5, operations on functions. Pretty short lesson. Going to learn a neat new way to use our calculator. The y equals menu has been pretty good so far, but we're going to learn how to use that a little bit quicker without having to use the graph. So that's going to be really nice. This lesson definitely is one that should just make sense. All right, so just like with polynomial functions, in Chapter 4, we worked a lot on adding, subtracting, multiplying, and dividing those functions. We can do the same thing with any function. Okay, so if we are taking a function just in function notation, like f of x, g of x, h of x, we can define new operations, regardless of the type of function, that are f plus g of x. And that just means we're taking the first function and adding the second function to it, essentially combining like terms. Subtraction, same thing. Multiplication, just what you'd expect. We're multiplying those two functions together. With polynomials, this would mean crazy amounts of foiling. And then division, again, same thing, but we can simplify by factoring and stuff like that. We're going to explore that more in Chapter 7. But again, this idea of taking our function notation and adding different functions together is something that really allows us to easily express these operations. All right, our graphing calculator, like I said, it'll be a big support for us today. We can use y1 and y2, enter the functions there, and then in the calculator screen, we can actually type in y1 followed by parentheses with an input if we wanted to evaluate that. So to get to y1, typing that into our home screen, giving you the commands there. So the vars key for variables. It's just underneath the arrows on your calculator. Then we'll toggle over to y variables and choose function. That'll allow us to use y1 and y2. All right, so the first task, just by hand, find f plus g of x, f minus g of x, state the domain of each. It's important to realize that the domain of the function we get after we operate on it, it is not the original domain of each. So like sometimes there's some extra work, especially with radicals, like you can see here in number 4, where we need to make sure that both domains of the original functions are satisfied. Because if they are not, and we try and combine them together, we can't properly combine imaginary numbers with real numbers. So we want to be sure that we're working with defined areas on our graphs within our functions. So here, f plus g of x. It's a new function formed by adding f and g together. It means just what you think it would. F of x, that's the cubed root of 2x, plus g of x, that's negative 11 cubed root of 2x. And let's see what that function is. We have definitely got some like terms here that we can combine together. I've got a couple of cubed root of 2x terms, so I could combine those together. Think of this as 1 cubed root of 2x. Take away 11 cubed root of 2x's, we get negative 10 cubed root of 2x. Okay, so that is my function f plus g of x. And then let's state its domain. Well, originally we could not have, for f and g, we could not have x's that are less than 0. If x was less than 0, that means our radicand underneath that radical would equal 0. But wait, we're in luck. It's a cubed root function, and cubed roots actually allow negative numbers. So I was a little bit hasty in saying x had to be less than 0 in this case. Our domain is going to be all real numbers. I could plug any real number into f, I could plug any real number into g, and I would get a real output. So as a result, my f plus g of x has a domain of all real numbers. Okay, next, f minus g of x. Again, I've got my 1 cubed root of 2x, that's function f. And now I'm subtracting negative 11 cubed root of 2x. Again, we're fortunate that those are like terms, but it's not a huge deal if they aren't. Here I end up with 12 cubed root of 2x's. If I have 1 and I take away negative 11, I end up with a positive 12. And just like before, since f and g, both those cubed root functions allow all real numbers as inputs, this difference of f and g also has a domain of all real numbers. Okay. Now what we're supposed to do is take those and those new functions that we have and evaluate them. They've given us an input of x equals -4. So I'm trying to find f plus g with a -4 input. Well, I've got my f plus g function. It's -10 cubed root of 2 times -4. And underneath that radical, we've got a -8. That's okay. It's a cubed root. So -10 times the cubed root of -8. Well, cubed root of -8 is -2. Negatives survive cube roots. So I'm taking -10 times -2. That answer should be 20. Plug a number in, get a number out. Let's try our difference. F minus g, if I input a -4 into that, now I have 12 times the cubed root of 2 times -4. And once again, that's allowed. It's like taking 12 times the cubed root of -8, which is like taking 12 times -2. We get -24 for that. Not too bad at all. It makes perfect sense. Next, find f times g of x and f divided by g of x. State the domain of each, then evaluate f times g and f over g at the given x value. Okay. First order of business. What I would probably do, and this is just my own interpretation of this, function f is 4 times the 4th root of x to the 5th. And g of x is -2 times the square root of x. I would change those rational exponents into radicals. For me, it just seems like an easier way to simplify. We don't have to do it, but it just makes more sense for me to see it that way. Okay, so now f times g of x what that's going to be is 4 times x to the 4th, or x to the 5/4, I should say, times -2 times the square root of x, and I'm going to call that x to the 1/2 here, because although I'm thinking of them as radicals, multiplying them together is easier to see with exponents. Okay, and what I get as a result, multiply the 4 times the -2, get -8, and I've got the same base of x being raised to 2 different powers. I can add those exponents together. That is 8x to the 5/4 plus 2/4 7/4 power, or 8x times the 4th root, sorry, -8x times the 4th root of x to the 3rd. Okay, and if you remember our simplifying endeavors in section 5.2, that's because x to the 7/4, the 4th root of x to the 7th, can be thought of as the 4th root of x to the 4th times x to the 3rd. We do get some simplifying to happen there. So that's how I wound up with the radical that I did. Simplified function. Okay, now domains. Eesh. Let's look at the domain of function f. And here's why I thought of it as a radical. If I plug in an x value that is negative into that little function f, it's going to be raised to the 5th power, raised to an odd power, which keeps it negative. And then I would try and take the 4th root, an even root of it. So I cannot have x's that are less than 0 go into that function. The domain of f is all x's greater than 0. And then, of course, function g, same stipulation. The only x's I can allow in can be greater than 0. We know that's what a square root function should accept as a domain. So the domain for this function f times g of x is all x's that are greater than 0. Those are what I can safely plug in to both f and g, and thus also f times g. Okay, so that does it for the multiplication. Now let's look at the division. F divided by g of x. Well, that's 4x to the 5/4 over -2x to the 1/2. And again, our rules of exponents are going to make this math easier to clean up. But again, finding the domains, it was easier to see them as radicals, I think. So I've got the 4 over negative 2. And then x to the 5/4 minus 2/4, that would be x to the 3/4. Okay, we can use those properties of exponents, subtracting the exponents when we have division with the same base, of terms with the same base. So negative 8, or negative 8, I'm looking up above, negative 2 times the 4th root of x cubed. So there's our f divided by g of x, and yet again, because of the domains of function f and g, even though it looks like I could plug in something just fine into that, or it may look that way, I can only accept x's that are greater than 0 for that domain. And all that's left to do is to evaluate those with our input of 4 that we've been given. So f times g of 4, I know the function, now I just need to input it. That's negative 8 times x, which our input is 4, duh, times the 4th root of, in this case, 4 cubed, 64. And all that's left to do is simplify. So let's see, negative 8 times 4, that's negative 32. And the 4th root of 64, well, let's see. I know that 64 can be thought of as 2 to the 6th. And I'm just kind of spitballing here. We could definitely use a calculator to get this right away. But negative 32 times the 4th root of 2 to the 6th would be negative, I can take a 2 out of that. And then I'll have the 4th root of 2 squared, which is the same thing as to the 2/4 power, so negative 64 times the square root of 2. And again, a calculator could drastically help us with that. Just kind of working through the math on my own. Sometimes it's fun to do it by hand, the old-fashioned way. And lastly, f divided by g of 4. F divided by g, found that function to be negative 2 times the 4th root of our input cubed and our input 4. So we see that same 64 underneath that we saw with f times g. That's negative 2 times, what do we find that root 64 to do? Well, we pulled out a 2, and then we had square root of 2 left over. Should have negative 4 square root 2. And now, I just want to be sure, because I did a lot of work by hand there. I just want to check, and the next example is involving the calculator as well. So I'm just going to take a second and pull up the calculator just to check that work that I did. Okay. So inside, I've got this function f of x, and this will be a little precursor into what we're doing in the next example. And that f of x was 4x to the 5/4. So I'm just going to type that in, 4x caret in parentheses 5 divided by 4. y1 is going to represent f. y2 is g, that's negative 2 times the square root of x, or we could put x to the 1/2 if we wanted as well. So if I quit to my home screen and then do that vars over to y-vars function, y1 is f of 4, and I multiply that by vars over y-vars function y2, that's my g of 4. This should give me the same thing as this negative 64 square root 2. So let's see what that is. It comes out to a decimal. Let's see what negative 64 times the square root of 2 is. Hey, look at that. So by using the calculator, we can also evaluate that very, very quickly. Let's check our division. So vars over y-vars function y1 of 4 divided by vars over y-vars function y2 of 4. we get negative 5.6568. Let's see if that's negative 4 times square root of 2. Negative 4 times square root of 2. How about that? So our answers check out either through a calculator or by hand. Excuse me. And we've kind of got a nice little glimpse at what the next example is. So in the next example, use a calculator to find f plus, f minus, f times, and f divided by g of x, respectively, when x equals 5. Here we go. And we'll round to 2 decimal places for each one. So I'm going to go back into y equals. My f of x is 4x to the 1/2. Clear out what was there and type in 4 square root of x, just because it's faster, I think, to type it in that way. And then I'll clear out y2. That's going to be my new function g. That is 6 times x to the 3/4. So x caret parentheses 3 divided by 4, or 0.75. We can do that as well. Let's quit to the home screen. We're going to find each of those when x equals 5. So vars over y vars function, y1 is f of 5 plus vars over y vars function y2 of 5. Okay, so there's my addition, 29.01 if we're rounding to 2 decimal places. Now let's do the next one, vars over y vars function y1 of 5 minus vars over y vars function y2 of 5. Enter. Get negative 11.12. Let's do multiplication. I get 179.44. And lastly, division. I hope this all fits on the one calculator screen here. I don't think it will, though. Okay, there we get our division result, 0.45. Okay, so give me 1 second. I'm just going to copy that to the PowerPoint. So we can see those decimal outputs. Obviously, the line for addition got cut off as I did all 4 of them on the same screen. But you can see we got our function, and then in parentheses afterwards we put our input in place, and we got those 4 decimal answers for addition, subtraction, multiplication, and division. Pretty slick. Our last example, from 2005 to 2009, the numbers of cruise ship departures in thousands from around the world, that's our function W, and Florida, that's F, can be modeled by these 2 cubic functions, where T is the number of years since 2005. So find W minus F of T. Well, here, what we're doing is we're just taking W of T minus F of T, and since I know those 2 functions, I am just combining like terms as if I were subtracting away each term from function f. And the result I get, we're going to have to use a calculator to combine these like terms just because of the decimals involved. We could grind it out by hand, but that really wouldn't be that much fun, even for a math teacher. So our new function, w minus f of t, what I came up with was negative 18.333 t cubed plus 77.72 t squared plus 372.5 t plus 6,615. Okay, so we ground through all that work. We combined all those like terms. What does that mean? Well, let's think about the context of the problem. Usually when we have to explain or interpret, it means that we have to apply units to a situation. So here, our new function represents, okay, we got the outputs here. The outputs are representing all the cruise ship departures from around the world, but we've taken away those departures from Florida. We've subtracted them out. So it is all departures of cruise ships since 2005 that were not from Florida. Because we subtracted away F of t, we took away all of the different departures that were from Florida, leaving behind the cruise ships not from Florida. If you get done with a problem like that, you look at it initially and think, oh man, this is a really complicated problem. But then you get done and you're like, oh, that was it? Really? That's what functions are for. They explain our data. Here's a look at your homework assignment for section 5.5.